Today is the day we start talking about and hopefully wrap up the subject of lenses. And then this is the second to last lecture. So next lecture we'll do diffraction and interference, and then we've got a review session, and then it's finals week. So if you have questions, jump on office hours or interrupt me. That's perfectly fine. So having said that, so let's take a couple of steps back. So when we were talking about mirrors, we had this very basic description of what a mirror is, and it's just a flat piece of metal, and that piece of metal, if it's flat, it will reflect waves, electromagnetic waves, such that when the wave is coming in at some kind of an angle with respect to the normal, it gets reflected in the opposite direction with the same angle. So the incident and the reflected angle are equal, except they're on the opposite side of the normal to the surface. And then we use that principle to derive the mirror equation, which allows you to calculate what happens when you form a mirror that has a curvature, so it's a parabolic surface. And in that case, if you have all parallel rays, they'll all converge into the focal point. And we use that, plus the fact that there's something about this special ray that we use that to calculate where images form when you place some kind of an object. Now, parabolic mirrors, of course, are ubiquitous. They're also used as things for astronomy. So, for instance, I don't know if you heard, unfortunately, Arecibo, that big radio telescope, unfortunately collapsed yesterday. And but it was a really big parabolic mirror, in effect. And the bigger, the more signal it can gather. So that's where we ended up with when we talked about mirrors. We had curved mirrors. So fundamentally, on physics level, we said there's a boundary condition. So there's something special about a metallic surface such that when electromagnetic waves hit it, they interfere with it they interact with it in a manner that is described by physics. And then afterwards, we will be able to deduce that therefore the incident and the reflected angle are the same. So today we will try to follow the same logic when we start talking about dielectric media. So dielectric media, we're talking about glasses, water, 2-degree air, and they're usually characterized by the fact that waves, electromagnetic waves such as light, they are they propagate in them with a speed that is lower. So we'll have to come to some kind of understanding of what that lower speed means. So if you think about it this way, let's say you have a wave light that is traveling through air. It's going to be pretty close to the same speed as in vacuum, but then when the wave hits the water, it's going to slow down, because for light it's a little bit more viscous, if you want to think about it that way, right? Because it takes a little longer to go through it. So the thing that we'll need to do is we'll need to establish some boundary condition, and the boundary condition where we have the interface of air and water, for instance, or air and glass, it's a little bit more tricky to do than it is for mirrors. But we'll try to really take a couple of steps and look at the bigger picture, and hopefully you'll have a pretty good understanding of what's happening really physically at the interface. And then at the end, we'll be able to generalize that and say, okay, now if we introduce some kind of gentle curvature in this material, then we can talk about lenses. And when we do lenses, then we could do optics and image formation. We could talk about diopters, and also why some people need glasses. Okay, so that's the plan for today. So today we'll talk about optics in dielectric media. So we know that electromagnetic waves are transverse electromagnetic waves, and the speed is 1 over epsilon naught mu naught, and that's the speed of light. Now for media that are dielectric, the way we incorporate that usually is by changing this epsilon. So we would change this epsilon naught, and we would make it some kind of an epsilon r, kind of epsilon naught. So epsilon r is kind of a rescale factor. This is usually, greater or equal to 1, because you cannot go faster than the speed of light. And this is our previous epsilon naught. And then as a result, you get some kind of a v, which is going to be c divided by the square root of epsilon r. All right, so all it does is it kind of slows things down a little bit. Okay, so what does that mean in practice? Well, let me some drawings. So, for instance, we have a wave that's traveling in this direction. I'm going to try to do this geometrically accurate, because last time when I didn't do that, my drawings were all messed up and I have to go back and do it again. So there we go. So we say we have a wave, and the wave is traveling in this direction. So then at some point in time, we take a snapshot and we're saying, okay, tell me where all the phi is 0 crossings are, right? So this is where the separation is lambda between those points. And that's at some kind of point in time. And then at some point later in time, we will find that those things will have moved over to the right. So I think I probably have enough, but just in case anyway. Okay, so this is traveling in this direction with some kind of a speed. So let's call this, some kind of a speed, v, and then we can quantify the wavelength here on this side. Okay, now we have, let's say, medium number 1 here. So let's say we can call this vacuum. And then we have medium number 2 here. All right. So we can call it glass if you want. So it slows down. So because it slows down, the speed is lower, and therefore the wavelength is also lower because the frequency is not changing. So I'm going to make a very extreme example. All right. So I want to say it goes down quite a lot. The material is very sluggish from an optics point of view. So that's slows it down so much that the wavelength is lower by a factor 2, which means that epsilon r is 4. That's ridiculous for optics, but there are materials that do that. So that's fine. So we're not changing the wavelength. We're not changing the color, but the wavelength absolutely does change. And but so far so good. This is just what happens when light travels from one to the other. And there's there's another wavelength here. So this is now lambda over there. And it goes still in this direction, but now with some other kind of a speed, v. And at some point, if we take so this is at t is equal to 0, for instance, is when we start our stopwatch. T is equal to 0. Now at some small point later, all of these will have moved over to the other side. So this is just a snapshot. Okay, so this is all fine, right? There's a boundary between the two materials right here, and that's what's happening. So let's summarize. So we have a lambda incident, and we have a v incident, and we have an f incident. Now The frequency doesn't change, right? So we're assuming a material that doesn't change the color. So I'm going to call this lambda t for transmitted. Some people would use R for refracted, except we already use R for reflection, and it's confusing enough as it is. So I'm T transmitted. Okay, so this is transmitted, and this is incident. So incoming, outgoing. All right, now I forgot to press unpause when I was doing this really cool arts and crafts. Okay, I apologize. So for posterity, when this line hits this boundary, there's a null here. So the electric and the magnetic field are 0, and we require that the electric and magnetic fields are continuous, which means if it's 0 on this side, it's also 0 on that side, which means that we accommodate that for that by changing the angle. So if the angle here of between the propagation, let's call that theta I, and let's call that theta t, you see that those angles are not the same. Okay, so how do we relate these? Well, there's just a bit of trig involved. So if the distance between here and there is the same on the left side as it is on the right side, we just need to analyze this problem in terms of trig. So if we call this distance from here to there, we call that the tangential wavelength. So we're going to call this, oops, okay, we're going to call this lambda tangential. Then there is a relation between lambda tangential and theta and the speed. So let's see what that looks like. So we have this lambda, we've got this angle, and we have the original lambda, which is like this. Okay, so lambda tangential and the actual lambda make a right angle triangle, and lambda tangential and lambda, that ratio is equal to, well, let's see, so it's over that. Yeah, that's the sine of theta. So why is that? Well, it's because there's an angle here that's the same as this angle. And if this is theta, then this over that, that's the upright over the hypotenuse, is your sine of theta. So lambda over lambda tangential is sine theta. And now we require that if lambda is the same, so we require that lambda incident is lambda transmitted, then that means that tangential, that means that lambda incident over sine theta incident is equal to lambda transmitted over the sine theta transmitted. Okay, now let's reverse this, and let's remember that lambda is so I forgot to write this down. So C is lambda F. Okay, so because C is proportional with lambda, I can replace this with the speed in the medium. So we can just say this is V incident over sine theta incident, because we don't change the frequency, so we can just swap these out. Oops, transmitted sine theta transmitted. And now, because the speed is proportional to, where did I write that? Oh, okay, I guess I didn't write that. So because the V is proportional to 1 over the relative dielectric constant, I can rewrite this, and I can make this 1 over square root of epsilon I sine theta I equals 1 over square root epsilon t sine theta t. And now finally we can flip this over, and we'll call n, by definition, the square root of epsilon r. Then we get n I sine theta I is equal to n t sine theta t. And this, ladies and gentlemen, is Snell's law. So this n is unitless, because epsilon r just only changes it only changes the magnitude, but it does not itself carry units. So n here is the index of refraction. I need more space. And it's basically a way to say how much the speed changes, right? Because people got tired of writing the square roots. So for instance, n vacuum is 1. N for water, 1.33, et cetera, et cetera, et cetera. Okay. So let's do, so theta I is, let's call it 45 degrees, and air, and just use n is 1 for air. And the transmitted medium is water. So calculate what is theta t. So let me bring this, and I'll give you the code. So yeah, most of you had that right. It's not complicated. So using these, you just get a theta t. It's 32 degrees. Okay. So in practice, what does that mean? Well, let's see what happens if this is actually going on. So it's the same set of same two media, but now we're not looking at a medium that is we're not looking at a medium where the boundary is vertical, it's horizontal. So let's call this air, and let's call this water. So let's say there's a fish here. That's my fish. And I'm standing over here. So this is where the shoreline is. And I'm trying to figure out where this fish is. So the thing to remember about Snell's law is that we label the incident and the refracted or transmitted medium, we label them separately, but there's really nothing in the way that we got to Snell's law that requires us to assume that the wave is traveling either from water to air or from air to water. So in fact, in Snell's law, if you swap the incident and transmitted, you obviously have the same expression. So long story short, it doesn't really matter whether you're using a flashlight and you're trying to illuminate this fish, or the fish is illuminated from below, and some of these rays will actually hit your eye. Now, if let's say if I'm looking here, it probably ends up being something like this. So you'll see the fish here because that angle becomes smaller in air than it is. So in this case, this is actually theta t. In this case, this is theta I. So that's why sometimes in Snell's law, we'll just say theta sine theta 1 n1 is equal sine theta 2 n2. Just we don't really care too much about which one is the incident and the reflected. So, sorry, refracted. Okay, so what does that mean? Well, so you see the fish, even though it is here, you actually see it here. So for instance, if you were to be spearfishing, you would see this would be fish prime, and this would be fish. So image formation is important here. So if you're spearfishing, you want to make sure that you correct for that. Yeah, I don't know anybody who does spearfishing. Okay, good. Now let's see what happens if we have this fish and we move it around a little bit. So for instance, if this theta I becomes bigger, then theta t becomes bigger as well, right? So if this one becomes bigger, then this one becomes bigger as well. So there's a point where theta t is 90 degrees, and theta I is not at 90 degrees, it's probably like 54 degrees or something like that. So there's an angle beyond which you cannot see the fish anymore. Or looking at it from the fish point of view, if the fish looks this way and it's beyond that angle of 50 odd degrees, none of the light that it sees is coming from outside anymore, but this light is actually coming from the bottom. So for that angle, this surface becomes a mirror, and that angle we call the critical angle. So it's the angle beyond which the light cannot leave the medium. So what is that? Well, we have an n water sine theta water, and then we have an n air, sine theta air. So because n water is bigger than n air, this product needs to be the same. So if this becomes bigger, that means this is smaller. So if theta water is smaller than theta air, as you can see here, right? So this angle is smaller than this angle. So that angle where this angle is exactly 90 degrees in air, so the theta air is 90 degrees. In that case, this is 1, and then we have a sine theta sub c for critical is n air over n water, and then theta c is the arc sine of that, n air over n water. And that's what we call the critical angle. And that's important. This critical angle is actually also used quite a lot. So, for instance, if you have a glass cable, let's say an optical fiber, and you try to get light to go through, the light's actually guided by this by this fiber, because the light that is trying to escape is kind of reflected back. And there are extra things that you can do, but that using the fiber as a guide for light is actually very powerful phenomenon, and that's what's used in optical communications. So then what you use is you take a tube made of glass, plastic, something, and then usually you put also extra coatings on it to really help you with this. And then the light that you send in on one end actually ends up goes to just travels for a really long time. And fiber optic communications are still one of the best ways to get signals from point A to B at the speed of light, although a little bit attenuated by the fact that it's moving in a medium where the speed of light is a little lower. Let's talk about lenses. All right, so what is a lens really? Well, it's this material that when you can make it out of glass, you can make it out of something, and it's got this curvature built in. So let me see if I can use. Okay, so I'm going to super exaggerate the curvature. Okay, oops. So let's say we call this glass, and we call this air. All right. Now let's say we have a ray of light that's coming in here, and it's let's say the one that's over here. Now at the point where it hits this surface, we need to evaluate that incident angle with respect to the normal, but at that point. So that means that if I have a ruler, I should just use it for everything. I don't know, I'm getting sloppy. Hang on a second. So because glass has a higher index of refraction, that means this angle becomes smaller on the other side. So let's just eyeball it. I don't know exactly what it is, but it's just the diagram. Okay, so this angle now is smaller, right? So the light comes this way. This is the normal. So that's for a ray of light that hits this point of the surface. But for instance, if I take a ray here, I am much closer to the part where the surface is perpendicular. So this angle is therefore smaller. So therefore, this angle also becomes smaller. So it becomes like this. Okay. Now, I hope that you see that these rays, even though they were parallel on this side, over here now they are converging. And what does that mean? Well, that means that at some point these are going to meet in a point. But usually we don't use lenses this way. We usually make a lens out of a material that is shaped in, let's say, another nice surface. So that means that the point now where this ray hits the surface is here. And that means that now the normal is like this. And now it's going to bend away from the normal because the angle in glass is smaller than the angle in air. So I'm just going to eyeball it. Let's call it something like this. So this angle is bigger than this angle. And now same thing for this ray. So let's call it like this. And the normal is like this. This angle becomes bigger over here. So let's call it something like this. I'm going to eyeball it because it's supposed to actually go through the same point. Okay. So this light goes in here and then keeps going. And then keeps going. There you go. So if you shape these surfaces correctly, and off the top of my head, if I'm not mistaken, these are again supposed to be parabolic surfaces, but I could be wrong. That means that all of these rays, they will end up here in the focal point. And that's really the basic thing that makes a lens work. Now, the funny thing is that you might expect, because they converge because they hit the angle here. They hit the surface here at a different angle because there's a physical distance between this point and that point, and between those the curvature goes like this, so it goes away. You might be tempted to intuitively expect that the angle goes back to what the original was, but except it doesn't work because here the curvature is going in the opposite direction. So if you shape this correctly, you would call this a converging lens. So call this a converging lens. So I'm going to make it like this. Air, glass, air. Oops. There you go. So this is a converging lens. And there are different ways in which you can make a converging lens. For instance, you could do it like this. The way I drew it, you could do it like this. This is plano convex, or you can do it. You can even do something like this if you want. Oops. So they both curve this way, but the lens is thicker in the middle than it is on the side. So all of these will have, all of these are converging lenses, right? And you can make this super exaggerated. Now this, of course, this should be very familiar to you. For instance, if you've ever had a magnifying glass is just a simple converging lens. And if you, for instance, do this outside and you let the sunlight hit this, all of these rays coming into this central point means that all that sunlight gets concentrated here if you choose. And then if you have some kind of a surface here, you could actually heat that up and fires can get started that way. And of course, I don't condone it, but it does happen. So that's a converging lens. Now, a lens with a curvature that is actually going in the opposite direction. So for instance, would look like this. And we can ask ourselves the same question: what happens to a beam of parallel light? And we again have to evaluate the angle that it has with respect to the normal. Now it's going to bend towards the normal. That means these rays get bent up. Oops. And you see that these rays are actually diverging already, but let's see what happens if we actually put another surface here. So this is the interface where we go back to air. Now we again have to evaluate the angle with respect to the normal. And that means that if you look at this point here, it's going to bend away. This might even be the critical angle already, but this angle is bigger on the right side than it is on the left side. So this light actually appears to be coming from a point over here on the left. And we're going to call that the focal point. But because this focal point is on the left and the light that comes out is diverging, we call this thing a diverging lens. So this is a diverging lens. F is, because it's on the other side of the mirror, is less than 0. And they can have multiple shapes. So for instance, you know, your glasses might look like this because it and now let's fix this one. So it has to bend towards the normal. So let's do it like this. And then when this ray hits the surface, again, we need to evaluate the angle with respect to the normal. And it's going to bend away from the normal further because that angle increases. So let's call it like this. And now I'm going to cheat because I want it to actually come from the same point. There we go. And here's the theta. And these are connected. And these are connected. So this is a diverging lens, right? So it could be shaped like this. Could be like the one I drew. As long as the thickness here, so it's thinner in the middle. And in fact, if you have eye prescription and you are nearsighted, you will have these kind of glasses that you can tell because your glasses will be thicker on the outside than they will be on the inside. If you wear glasses, you can now decide whether the glasses that you have are converging or diverging. Most people have a need for a diverging lens, and you can tell because if you look at your glasses, you can tell that they're thicker on the outside than in the middle. So those are diverging lenses. Okay, so let's do geometrical optics with these. So geometric optics. If we simplify our lens a lot, what we actually do is we don't draw this as a 3D object anymore. We actually draw this as an object like this. So this is a converging lens. And if we send a parallel beam of light through, light goes through this focal point. All right. So it's if we have, let's say we have somebody standing here, and now we can ask ourselves again, like what we were doing for mirrors, we can ask ourselves, okay, where does the image form? So let's see. So we again use one ray that goes like this, and this is the P ray, and the P ray goes through this point and then keeps going. And the C ray hits the center here, and because it hits the center, it goes in a straight line. That's the C ray. And the image forms here. So, okay. So we do the same thing we were doing before. So we're going to call this the image distance. So that's d sub I, and we're going to call this the image height. And we're going to call this the object height, and we're going to call this the object distance. And now we can use the same triangles to relate these things to one another. So the first triangle that we'll use is this one. So it's this one. And then paired with this one. So our red triangle, this angle is this angle, and this is a right angle triangle. So that means that the tangent of that angle is h over d. So tangent of this angle is equal to the tangent of that angle. So h over d is equal on both sides. So that's h o over do is h I over di. Except we're going to use the same definition that if h is negative, corresponding compared to this, we're going to call it a negative number. So even though this angle says that it's this over that, but if h is a negative number, so this in this case is a negative number, then we'll fix that by using this. Okay. The second triangle we will use is one second. Our second two triangles we'll use are this one and this one. So for the green, so we have two triangles, and the tangent of this angle is the same as the tangent of this angle, so we get the same two equations. So in this case, the tangent is this over that, and this over that is hi over f, sorry, ho over f, equals, okay, now this tangent is this plus this over this. Now this is hi, and this is in absolute value, sorry, this is ho, this in absolute value is hi, except we're going to change the sign. and then that is divided by di. Okay, now we'll combine these two. We'll combine these two. Now we want to get an equation that only depends on distances. So that means we want to figure out a way to eliminate these h's in favor of d's. So let's do that. So I'm going to divide out my ho. So now I'm going to get 1 minus hi over ho over di. And now hi over ho is, according to this, minus di over do. So that's 1 plus di over do over di. And now you see that I can just distribute this out. So I'll get 1 over f equals 1 over di plus 1 over do. And this, ladies and gentlemen, is the thin lens equation. All right, and this equation we use for the magnification. So we'll say the magnification, and magnification is a number that is unitless. The magnification is di over do is minus hi over ho. So there's a minus there. All right, so let's see if this works for the numbers that I put in. So in fact, in this case, I would call, if this is 1 meter, I would call do 2 meters. So do is 2 meters. Now, that means that di is, using the thin lens equation, I'll bring my di over to the other side. Sorry, I'll bring my do over to the other side and then I'll invert it. So it's 1 over f minus 1 over do to the power minus 1. All right, this is 1 minus 1/2 to the power minus 1 is 1/2, inverted, is 2. Woohoo! That's looks pretty good. If this is 2 meters, this is 2 meters. That's pretty good. Now, if my height, so our height is 2 meters, then the height of the image is using this equation. It's height of the object with a minus times di over do. So it's minus, because di and do are both 2 meters, minus 2 meters. And that looks pretty good. This height is pretty much the same as this one. This height looks pretty much the same as this one. So that's pretty good. Okay. Now, the terminology. So the image is real because di is greater than 0, and the image is inverted. Because hi is less than 0. And I think I put the minus sign here on the wrong side. I do apologize. This is supposed to be here. So it's actually m is less than 0. Okay, now compare this to the mirror equation. It looks actually identical, except there are sign conventions here that are different. So when we were talking about mirrors, when di and do were on the same side, we called both positive, right? So we had an object here and then a mirror that was curved, and then the image formed here. If they were on the same side as each other, then we called both of those positive, and the image that formed was real. In this case, the image is formed on the other side, we call both DI and DO positive, and the image here is real. So DI is greater than 0 means the image is real, except I want you to recognize that DI is actually measured to the positive to the right, whereas DO is measured positive to the left. So DI and DO are not two vectors in the same coordinate system, if you want to think about it this way. Whereas when we were when we were doing mirrors, that was absolutely the case. Now let's use a diverging lens. So do the same thing, except in this case, this is a diverging lens, so it's thinner in the middle, and we also can put a minus sign here. And the focal point is here, so it's on the other side. So let's say I'm here. 6. Yeah, that's fine. Okay, so I'm here now. Again, we do the same construct. So we look at the P-ray, and when it comes out, it actually ends up coming out as if it is coming from the focal point, but the focal point is actually on the other side. So that's this ray. And the C ray goes like this. Now the image forms where these are, that's where the image forms. Now this is a virtual image, right? Because this thing is on the same side, meaning you cannot put a projector screen here. But to an observer that is standing here, this observer would see this person standing there, not there. So that's what we would mean by that the image forms here. And we could use the exact same same triangles and same conventions with the following modifications, that in this case, F is a negative number. So there's signs going to fly all over the place. So this would now be a negative number. And because HI and HO are both positive, but that's fine, but they're both on this side. But now DI is a negative number. All right, so we would find the same equation. So again, we would find the thin lens equation. We have 1 over F equals 1 over DI plus 1 over DO. But for a diverging lens, F is less than 0. Okay. So let's see how that works out in numbers. So if this is a, let's call F again, let's call it 1 meter because I like doing that. So if this is 1 meter, then maybe DO is 3 meters. This is a diverging lens, so this is negative. So DO is same thing, 1 over F, 1 over, oops, DI minus 1. All right, here we go. So this is minus 1 over 1, so that's minus 1. Minus 1/3. All right. So it's going to be a negative number. Minus 1, that's minus 1 minus 1/3, that's 4/3 inverted, minus 3/4 meter. And that means the image is virtual because it is smaller than 0. And 3/4 seems about right. If This is 1 meter. This is 3/4. All right. And we would have the same equation for the magnification. So we'll have the magnification, which is going to be minus di over do is hi over ho. Okay. If we use these numbers, so di over do is minus 3/4 over, what did I say, 3 meters? Yeah, 3 meters. So that's plus 1/4. So this is greater than 0, so therefore it is upright. All right, so this one's negative, and this one's positive. And then if you, let's say you want to know, okay, if the object is 2 meters, then the image is about 1/4 of that. Okay, so let's talk about let's talk about optics for your eye. Okay, now if you go to an eye doctor, and I'm assuming most of you are wearing glasses, or at least know somebody who's wearing glasses. Usually they will tell you that oh, you now have -4. So my glasses, for instance, are -4. So what does that number mean? So that number actually has a unit, and I hate the fact that they never write down units. But for instance, your eye prescription would say, for instance, OD, OL, -4, -4. One is left, one is right. Is it OD, OL? I'll look that up. What does this number mean? This is actually in DPT. That's in diopters. So DPT is diopter, and it's 1 over f in centimeters. All right. So if you have glasses with a strength of -4, your focal length is going to be 1 over 4 in centimeters. So it's like 0.25 of a meter. Now, sometimes they will tell you something else with this. So for instance, they'll say plus 1/2 45 degrees. What does that mean? That means that you have astigmatism. So that means that your eyeball, if you look at the lens, so it's supposed to be constant curvature, right? So if this is your eyeball, I should have brought a ball. So you have a ball here. Where is the ball? I had a ball. Can't find it. Okay, so imagine a sphere. So you have a ball here, and now your light goes through, but the curvature is the same in this direction as it is in this direction. Now, if you have astigmatism, that means that actually the curvature in this direction is not the same as the curvature in this direction. And they are usually kind of rotated with respect to one another. So these two numbers mean this is your base curvature, this is the correction that comes on top of it, and this is the angle that describes the point where those cross over. Astigmatism is usually, it's not too big of a deal. So usually it just means that if you look very carefully at the lens, that curvature is a little bit more like this than it is like this. Those of you that have plus are they're called farsighted. So if this is negative, we call that nearsighted. And if it's greater than, we call it farsighted.